Now let's look at the Doppler effect for light. Recall the equation for sound. This equation does not apply for light simply because the speed of light is a constant according to Einstein's special relativity. And to simplify the equation, we're going to introduce two new terms. V refers to the relative speed between the observer and the source, and C refers to the speed of light. Now I have here a diagram showing a source moving towards an observer. Now for simplification, I'm going to assume the observer stationary, so the source is actually moving with the relative speed v, and I have here the first wavefront given off by the source when the source was at x, and I have the second wavefront given off by the source when the source has moved to a position y. The distance covered by the first wavefront is c, the speed of light, multiplied by t, the period of movement based on the observer. And for the distance traveled by the source, it will be v, the relative speed, multiplied by t naught, the period based on the observer. So effectively, the distance between the two wavefront is my observed wavelength. So I'm going to put that down. Observed wavelength is equal to ct naught minus vt naught, and upon factorizing t naught, I get this equation. Now t naught refers to the period according to the observer. I'm going to change this to the period according to the source, and therefore I'm going to subject it to a Lorentz factor according to this expression. So what would I get? I'm going to get Ts divided by the square root of 1 minus v squared over c squared. I'm going to rearrange this in this form. The square root factor, I'm going to bring it to a common denominator, and rearranging, I get c minus v over square root of c minus v times c plus v, and my denominator c square, when I square root, I bring it to the numerator as c, and c minus v divided by square root of c minus v, I get square root of c minus v. So this actually gives me this expression, c times ts. So this is the observed wavelength. So what about the observed frequency? Is equal to speed of light divided by observed wavelength, and that should give me c divided by c, can cancel, so I will get c plus v over c minus v times 1 over ts. Now 1 over ts is the frequency of the source. Now I'm going to rearrange this expression to a different form, like that. I will get 1 plus v over c divided by 1 minus v over c. So this is the expression for observed frequency. Now let's consider two cases. A, for the source and observer distance moving closer to one another, regardless whether the source is moving to the observer or the observer moving to the source, but the relative distance is decreasing. And this is when the relative speed is positive. So based on that, my expression follows as such. The equation doesn't change, and I'm going to re-express this to this form: 1 plus v over c power half multiplied 1 minus v over c power negative half. Using binomial expansion, I'm going to ignore the terms that comes after the second term. And I do the same for the other bracket and ignoring the terms that comes after the second term. And then when I expand this thing out, I get this, and again I ignore the third term onwards. So this expression gives me the observed frequency, and since this observed frequency is larger than f, I take f naught minus f is equal to fv over c, and therefore the change in frequency is f times b over c. So this is one expression for when the source and the observer distance decreases. Now let's consider a second situation where the source and observer distance increases. So for this case, the relative velocity is negative. So I will have this expression where it's 1 minus v over c divided by 1 plus b over c. Again, I use binomial expansion. I would get this expression, and I ignore the third term onwards. And I expand further, I get this expression. So since in this case f is larger than f naught, I bring f naught across, and I get f minus f naught is equal to fv over c, and therefore the change in frequency is fv over c. Now notice that for both expressions, they're essentially the same for case A and case B. This refers to the frequency shift. So at this point, I would like to point out for case A, where the source and observer distance is decreasing, it is commonly known as the blue shift. Whereas for the case where the source and the observer distance is increasing, is commonly known as the red shift. This is evidence to show that our universe is actually expanding, because the stars that's giving out the light is actually undergoing red shift. So it suggests that the stars are actually moving away from Earth. And I hope with this little explanation you will understand a little bit more about Doppler effect for light. Thank you.